A very important class of two-dimensional problems are projectile motion. Okay, and we get to employ the ideas of free fall, but with two-dimensional motion. So, for example, let's say we throw a ball. We have this ball. We throw it. So we consider the motion right after we throw it. And let's, for simplicity, say we throw it horizontally. So we've thrown it horizontally. So its initial velocity is purely horizontally. Gravity is acting at all times downward. Okay, the vector. And sorry for that little dot there, but I'm going to say it has a value AY, and I'm going to emphasize AX is 0. There's no acceleration horizontal. Nothing's pulling it or pushing it horizontally. Okay, so gravity's pulling it down. So we know, we've seen before, that this is going to cause a parabolic path. Projectile motion is indicated by a parabolic path. And we'll get that ball somewhere, and it'll hit the ground at a later time. So if we draw the ground here, we can ask a number of questions. So we could say, how far does it go if I know how high I threw it, how fast I threw it. We could ask, how fast is it going right before it hits the ground. We could ask, how long is it in the air. I'm going to go ahead and ask that question, how far? How far did I throw it? Okay, so no matter what question I ask, I need to start by defining a coordinate system and defining variables, listing knowns, and then thinking about my fundamental relationships, those equations that relate all the kinetic values. So with that coordinate system, I think that choosing the release point of the ball to be my 0 sounds reasonable, and I'll choose the direction of the motion to be positive x. And I could choose the ground to be 0 with up being positive. That's conventional. But I'm going to actually be a little bit clever with my choice coordinate system. I notice that there's no upward motion. This ball is only falling to the ground. The acceleration is pointing downward. So why don't I choose the release point of the ball's vertical position to also be 0, with down being positive. That makes all my values positive. I have an initial position that's 0, a final position that's positive, acceleration is positive, velocity is positive. So the coordinate system is mine to choose, and I think that's a little bit more clever to keep all my math clean. Okay, then we list everything that we know about it. In the beginning we have t0, x0, y0, v0x, v0y. Okay, we have all those values to start. Okay, we have our acceleration components, and I specifically indicated that acceleration x is 0 to emphasize there's nothing pushing or pulling there. Okay, and then finally over here I have my x or t1, x1, y1, v1x, and v1y. So I've got all those. And what do I know? Okay, let's suppose I know, well, first of all, I can choose my time. That's nearly always 0, but not necessarily. The problem could have otherwise. My coordinate system says that x0 and y0 are both 0. My vx is this velocity. It's purely horizontal, so it's going to be v0. v0x, I'll just say it's v0, and that can be whatever value I pick. v0y is what? It's 0. It's initially, at the very moment I release it, the only velocity is horizontal, so v0y is 0. Okay? Alright, I've shown here that ax is 0, and I know ay is equal to the acceleration due to gravity, and it's positive as I've indicated it. So ay equals g. That's 9.8 meters per second squared, but I'm going to leave it as a variable. If I get down to this end, I don't know t1. I'm looking for x1. Do I know y1? Okay. If I know how high it was when I released it, then y1 is that value. So let's just call that a y. Ooh, I have to be careful here. y1 let's call it an h. Okay, I was about to say y0, but we already have a y0. So we'll call it an h. So that's the height that I dropped it at. Okay, and do I know v1x and v1y? Well, I actually do know v1x, but technically that's because I'm in my head doing some kinematic equations. Just to emphasize, if there's nothing accelerating it left or right, that means the speed's unchanging. That means by the time it gets here, its horizontal speed is unchanged. Okay, so I technically know that one, but it's not useful to me. Okay, and I don't know v1y. Okay, now what am I finding? Okay, I'm trying to find x1. Okay, so I've listed everything I know that's useful, and now I can consider the equations. So I want x1. Now I know x0, I know t0, I know that ax0 is 0, okay, I know vx0, v0x. Okay, so I know a lot, but I don't know t final, which is important in those equations. So it's like, well, do I have to use the one without time? Well, that requires knowledge of the final velocities, and that's not going to help me out. I'd find because a is 0, and so I just get my final velocity equals my initial velocity that I already mentioned. And so the question here is that, well, I actually need to use in tandem my knowledge about the vertical motion with the horizontal motion. That is the basic idea of projectile motion and other two-dimensional motion, is that the motion's independent but connected by time. And so I don't know my t final, but I have enough information in the y, because I know the y final, I know y initial and y final, that I can use that to find time, and then use that time to find x1. Okay, so recognizing I have multiple parts. So I'm going to start, I am looking for x1, so I'm going to write out the equation that has everything in it that I know, wanting to find, or this unknown time, knowing I can find that another way. So x1 equals x0 plus v0x delta t plus, oh, I'm going to run out of room, plus 1/2 ax delta t squared. Let me clear that up. Okay. What things do I know? I know x0 is 0 by my coordinate system. v0x is v0, this initial velocity, which I can be given. The delta t is just going to be my final time minus 0. Okay, so t1 minus 0. And this acceleration, which is most important here, is 0. Okay, so that's great. So x1 is just equal to v0 times t1. Whatever that final time is. Now again, in this particular problem, many problems like it, you can say, I knew that off the bat. I knew that. If you knew physics before in high school, this is one of the most basic equations. Distance equals velocity times time. But that's not what's important here. We're going to use the process to be able to solve very difficult problems. Our goal is to habitualize the process so that you can find results you don't have memorized, the more complex and more realistic results. So I'm going to put a half box on this saying I've gone as far as I can with that one. Now what do I do next? I haven't used my vertical, so let's go and do that one. So if I write out my vertical equation, y1 equals y0 plus v0y delta t plus 1/2 ay delta t squared. Okay. And I recognize my y0 is 0 by my choice of coordinate system. My v0y is 0. Okay, it's not moving initially at the very earliest moment in the vertical direction. And so, and this is my value g, so I end up with y1 equals 1/2 g, and then delta t becomes just t1 squared. Okay. And so I now have a way of finding t1. So I can now use that to say t1 equals the square root of 2y1 divided by g. Let me extend that square root a little bit bigger. Okay. That again could be a result you already have memorized. And but again, let's think about process. And so now I can kind of half box that and say I've got what I need. I've got what I need to be able to find this. And so plugging this into this time, I can now solve for my final position. I'm going to go ahead and stop here because that's now just algebra. We can easily just plug that into there. But the main idea is I've used the different equations, the relationships, and connected them via time to solve for my unknown. Now think about this, how this could have been changed. I could have had a velocity pointing somewhat upward. So I did have a v0y. That would have been non-zero. That would have made this equation a little bit more complex, but I could have still used math to solve for my unknown time and to get that get a correct answer. And so the process is what's most important.